Hello everyone, so many wonderful familiar faces. And in the language of the Gadigal, may I welcome you all, Wujiri Gamarua, Dian, Babana, Gamarara, Gadigal Nagara. We are on the beautiful land of the Gadigal. And I pay my respects to their elders, past, present and emerging, and indeed to all First Nations people across this wonderful state of ours where we produce the best produce, the best wine, the best scientists, the best students, the best official secretary. I can't possibly say the best governor. This is what I'll describe as the fifth iteration of Ideas at the House, which is a concept which we conceived when I commenced in 2019, because it's very obvious to me that there are an extraordinary number of people, highly intelligent people in our community who we really should allow them to convey their knowledge to others. And there's also an extraordinarily wide group of people in our community who are just sponges in terms of wanting to receive knowledge. And so we thought, really, as part of the time I was governor, we should put those two groups together as often as we could. And hence we have this concept of Ideas at the House, and this is the fifth. The COVID restrictions of the last 2 years forced us online, along with the rest of the world. And tonight we've maintained that live-streamed format in addition to having you all here in the House. So to both everyone here, everyone online, a huge welcome to each and every one of you. The 5 ideas at the House so far have been the product of a collaboration. Science, as we know, is all about collaboration, so we got on the same bandwagon. It's been a collaboration between the Royal Society of New South Wales, ourselves here at Government House, and a range of generous and scintillating presenters, some of whom are in the room tonight. And so I want to thank the Royal Society for coming on this journey with us. The Royal Society, of course, the first scientific society in the Southern Hemisphere, and which continues through events like this to build on its rich tradition of enriching lives with knowledge and inquiry. The first president of what was originally called the Philosophical Society of Australasia was back in 1821. It was Governor Thomas Brisbane. His portrait hangs out here in the main hall. He's the willowy figure with somewhat of a wayward curl, and of course he has the astrolabe down in the corner of the portrait. He arrived in the colony in November 1821, and being an avid astronomer, by March of 1822, he had built a small observatory at what is now Parramatta Park. And imbued with the endemic curiosity of the scientist, Governor Brisbane, along with astronomers Charles Romker and James Dunlop, compiled the first catalogue of 7,385 stars of the southern skies, mapped in the European tradition, and not, of course, the black spaces of the Indigenous tradition. In 1822, Rumka also rediscovered Encke's comet, and in 1828 he was appointed New South Wales' first government astronomer, followed by his colleague James Dunlop in 1831. In 1828, the Surveyor General, Thomas Mitchell, many of these names will be familiar to you as a matter of history. Thomas Mitchell used the transit stones at the Parramatta Observatory as the initial meridian mark for the first trigonometric survey in the colony. Now, there's a lot of politics in play at that time. Some things change, some things don't. And Mitchell clashed furiously with Governor Burke. Mitchell was also adept at disobeying orders, one of the reasons for the clashes. He survived one of the last duels in Australia in 1851, only to die of pneumonia 4 years later which he picked up during a survey that he was doing down in southern New South Wales. Jump forward, a bit over 100 years or so, the Parkes Radio Telescope Observatory became world-renowned as one of, and in fact the most significant radio antenna used to receive live television images of the Apollo 11 land mooning. It's been a long day. Moon landing. Now, we all know that science is developing at a pace which is almost beyond human imagination. So where are we 50 years on from that moment in July 1969 when Neil Armstrong said, according to him, that's one small step for a man and one giant step for mankind? Well, 50 years on, this much I can say. Recently, researchers at America's National Institute of Standards and Technology gave their stamp of approval to some equations that might, in time, save untold petabytes of sensitive data from prying eyes. The existing encryption standards that underpin just about every online exchange of information are a bit, apparently, of gnarly mathematics, all designed to be well nigh impossible for today's computers to crack without just the right arithmetical key. But it's not today's computers that they are worried about. These scientists worry about a coming era, the era of quantum computers. Professor Simmons, what can I say? Do you have anything to add to that, I wonder, tonight? Can I say we are so delighted that you chose to come not only here to Government House tonight, but that you chose to come to Australia in 1999, becoming a citizen in 2007, and of course, being our wonderful Australian of the Year in 2018. And you are the leading light in Australia in quantum computing, indeed in the world. I understand that tonight may present, or at least once would have presented a challenge to you, not only because of the huge scientific brains in this room, but you used to be fearful of public speaking. One of the best public speakers in Australia, and she spent 4 years in high school moving her place in the classroom so that she didn't get caught in the English literature class having to engage in public speaking. Now, I reckon that's been a great scientific brain at work already. How you managed to navigate that, I have no idea. But are we not so pleased that it's been your passion for science that has long overridden that fear? And we are pleased not only for us this evening, because we are going to have a scintillating presentation, but for the countless number of students. And I heard many of those speeches and I saw many of those videos of you during that year of being Australian of the Year, when you were just exciting people about science generally. And we have a number of students, high school students, university students and PhD students in the room tonight. So on their behalf, can I thank you for telling them that there is a challenge, yes, but a great delight of doing hard things in science. So I welcome you to the stage, Professor Michelle Simmons, Scientia Professor, University of New South Wales and Sydney, Director at the RAC Centre of Excellence in Computing and Communications Technology, Founder and Director, Silicon Quantum Computing. I think, in short, scientific genius. Welcome to the stage.
I am incredibly excited to be here tonight, mainly because we had a breakthrough about a month ago. It was announced a month ago. We actually had it last year. And that was to present the world's first integrated circuit at the atomic scale. Now, that's something that our team is very excited about. It is a big goal, a big milestone of both our company, but also, I think, for humankind. And so I wanted to start the story, really, and try and explain why that's a significant outcome. And so I have to take you back, though, in history. I'm a big fan of history, back to 1947. So it used to be in those days that when you ran computers, you did use digital information, but they used to have computers that were made of valve radios. And so they were about this size, they were vacuum tubes, and they switched between on and off states. There were about 16 to 20,000 of those that made up a computer, and they were very unreliable. So when they broke, people had to find them, fix them. And somebody said, well, this is not good. This is just, we need compute power. We can see that the world's going to need it, but the way that we've built them is not great. And so they turned to something called a semiconductor, and a semiconductor is just a material that you can turn insulating or conducting by applying a voltage. And so in 1947, some American physicists and engineers got together and they made the world's first transistor. Now that was significant, it's since won the Nobel Prize, but they really didn't know what they were going to do with it at that point, because they realized to get a computer, they'd have to put lots of them together. And so it took them about 11 years. They integrated 8 different components onto a chip. It was a chip of germanium, and they made the world's first integrated circuit. Now that also won a Nobel Prize, but from a different set of people that made that. But they still couldn't figure out how to use it. And it was about another 5 years beyond that before they started making devices. And there they were using them as hearing aids, as amplifiers in hearing aids, and using them in calculators to do arithmetic equations. And then it was till 1971 before we had the world's first commercial computer. And so what's fascinating for me is that we've watched that. We've watched that history. And we've known that computers are fantastic. They allow us to communicate across the world. They've allowed us to send man to the moon and bring him back down again. Everyone has billions of transistors on their person at the moment. But despite that, they work in a serial fashion. They do calculations one after the other. And that means that even though we see them as being incredibly fast tools, there are some calculations, some problems they simply can't solve. It was Richard Feynman in the 1950s and 60s that said, if you wanted to understand the way the world works, then you have to build things at the same length scale that the world is made of. So you've got to get down to that kind of atomic length scale in order to understand it. And then he subsequently went on to say, at that length scale, at the very smallest length scale, quantum physics dominates. And if you could somehow harness the power of quantum physics, then instead of doing calculations one after the other, you could actually start to do them in parallel. And you'd get this massive increase in computational power. And that really spawned the world of quantum physics. Lots of people around the globe started to try and realize one, but the key thing is you have to make devices very small to access the quantum world. And so that really set our team off in 2000 to try and mimic that industry in the classical industry. So we were gunning for making the first single atom transistor to mimic the first transistor. And in 2012, we put a single phosphorus atom in place, and we found that we could encode information on the electron spin. We could measure a transistor on and off with one single electron spin. And I'll come to how we did that in a little while. That basically meant we've hit the first gate. So now, roughly about 11 years' time, we should get an integrated circuit made of atoms. And so that was what we were gunning for next. 2023 should have been the time that we realized that. We actually got that result at the end of 2021, so 2 years ahead of time. So that's why it's so significant. The team is super excited by this result. Many reasons. The first one is just the technological brilliance of being able to do that. And I'll explain what we actually did with that integrated circuit in a moment. But the second one is by getting that result, it's allowed us to see the next one. It's allowed us, when you've got something that significant, you can now see what the future holds. And that means within the next 5 to 6 years, we think we're going to have our first commercial product. And there's nothing more galvanizing for a team of researchers than being able to see the future and having that roadmap that's out there from the past. So now, let's go back. What did we do with that integrated circuit? Now, that one that was made in 1958, it didn't actually do anything. It just showed that they could put information in, perform some calculations, get them to talk to each other and get information out, but it didn't actually solve anything. With the integrated circuit that we made, we deliberately tried to find a problem where we could run an algorithm to solve something. And the problem we chose was something called a quantum analog simulator. We wanted to take Feynman's view and try and see if we could mimic the way the world was. And so we chose a polyacetylene molecule, which is literally a carbon single bond, carbon double bond, carbon single bond, double bond all the way through. And we chose a small enough molecule, so there's only basically 10 carbon atoms that we tried to mimic. And then we basically put our atoms in place with sub-nanometer precision to mimic the single carbon bonds and the double carbon bonds. So we're actually mimicking nature in the way that Feynman set out. Now, what's exciting about having something that small is that a classical computer can solve how electrons should flow through that molecule. So there are only 1,024 states, and we basically built two of these simulators. One where we cut it through a double bond, and another one where we cut the chain through a single bond. Now, we knew from the classical computer that we should see 10 conduction peaks in one of the devices and only 2 in the other one. So the exciting thing was when they made those two devices, they saw 10 beautiful sharp peaks and only 2 peaks on the other one. So it really confirmed that we had mimicked that polyacetylene molecule. Now, why is that exciting? For us now, we chose something we knew that a classical computer could do. So if we just now double the number of carbon atoms in that chain, we go beyond anything that classical computers can solve. So we've stepped off the edge of human knowledge. And that is also very exciting. So from a very fundamental point of view, we've built something that allows us to see and mimic the world in a way we've never been able to do. We remain the only team in the world that can manufacture things with that precision, sub-nanometer precision. And it literally meant we had to put the atoms in place and just literally change them by tiny amounts. We knew we had to put a certain number of atoms in place so that we could control the energy levels of each atom and all atoms up and down together to get the result we needed. So it's really quite a phenomenal technological challenge that we've met in that device. So now let's look forwards. What can you do with that device going forwards? What are the kind of problems that we can start to solve? And that's what's exciting. So we know that there are lots of problems out there we simply don't understand. We don't understand, for example, high temperature superconductivity. Now we can actually start to mimic that device and figure out how it's going to work. Looking at how we capture light from the sun and pass it down in artificial photosynthesis through these organic molecules, that's another thing we can start to look at. Bit by bit, we're starting to see there are lots of problems out there that classical computers just haven't been able to solve. One of those is turning nitrogen into fertilizer. So nitrogen is a very strong triple bond. The energy that's required to break that is humongous, and it's predicted that energy that's needed to break the nitrogen triple bond to get fertilizer consumes about 2 to 3% of the world's CO2 production. So if we could figure out how to get a catalyst to mimic another chemical that can break that bond more efficiently, it immediately starts to have economic and commercial interest. Beyond that, bigger molecules. You can start to look at drugs and imagine designing drugs that are going to target the problems that people have in the human body. Rather than going through 10 years and billions of dollars of drug trials, we can start to look at those kind of problems in real time by actually mimicking the molecules. So in the whole world of simulation, we've basically opened up this new technology that's going to allow us to see and understand the world in a way we never have before. Well, that's just one thing. Then people start to ask, what other things can quantum computers do? And there's been a lot of hype about quantum computers. They can solve all kinds of problems. And I think everyone that works in the field knows there's really just a subset of problems that quantum computers can solve. And so the way I kind of imagine this is there's two kind of vectors that we look at. One is the actual complexity of a problem, and one is the size of the problem. If we take a problem that's not very complex and very small, such as arithmetic, we can do it on a calculator, it's easy to do. We can then take more complicated problems that's still quite small, such as GPS routing or airline scheduling. And again, a classical computer can do that very well. But if we take a complex problem and a large problem, those are what we call intractable problems. And those are the things that classical computers just can't solve in a time frame that's useful for us. And an example of that would be the transport system. We've got planes, buses, cars. There's disruption in the network. Trying to optimize that system is something that a quantum computer could take from being a very hard, intractable problem and make it into something that we can solve in a time frame that's useful for us. Now, the code breaking you mentioned before, that's something that really kicked the field off. So it's well known that when you go into the bank and you type in your 4-digit PIN code, it's encrypted with a large prime number, so that it's very hard for someone to work out what those prime factors are and be able to get into your bank account. With a classical computer, if you take a 10,000-bit number and you encrypt your 4-digit PIN code with that, it's predicted it's going to take longer than the lifetime of the universe for someone to figure out what your 4-digit PIN code is. So we're all very safe. But one of the big encryption algorithms, or one of the big quantum computing algorithms, is code breaking. And that would be something we would be able to realize in about an hour with a quantum computer. So that's kind of kicked off the whole field of people trying to realize these large-scale systems that can do complex problems in real time that otherwise would take thousands of years. Now, obviously, that's now starting to move to many different industries. So it's not just the cryptography industry. I've talked about the transport system. I've talked about the health system and drug design. It literally hits pretty much every industry vertical. And so if you look at it, companies like BCG, the Boston Consultancy Group, have started looking at what is the financial benefit of having a quantum computer? What can it solve for our economy? It's predicted to be a much faster compound annual growth rate than the cloud computing has been. And it's been pretty much looked to be, by 2040, between a $550 billion and $850 billion industry to be able to get quantum solutions faster than classical solutions. But it also allows us to do things we couldn't do. So companies like Google are starting to look at it because they have so much data, they want to do fast database searching. If you imagine having an entry base with about 1 billion entries, roughly on the classical computer, you have to look at 500 million. With a quantum computer, it's only 30,000. If you've got UPS has come into this field because they realize if they could shorten the travel, the distance that their drivers travel by just 1 mile every day, they would save their company $50 million. So suddenly this industry is growing. There are over 70 different quantum algorithms are out there. People all across the world are trying to build a quantum computer, a practical quantum computer. And that's what's really exciting about the Australian effort. So when the field of quantum computing came to the fore and it moved from being a theoretical idea to actually practically we can actually start to control the world at these small length scales, there's a race everywhere. There are about 7 different physical platforms that you could build a quantum computer in. You can build it with something called Majorana fermions. You can build it with ions in a trap. You can use photons of light. And what the Australian team did back in 2000 was it did something that was quite simple, and I think, looking back, quite brilliant and bold. When quantum computing became popular, most of the research in the silicon field was done by the silicon industry. And so researchers at universities were always looking at what's the material that's going to come after silicon. It's going to be gallium arsenide, it's going to be graphene. There are all these different materials that will be faster and better than silicon. And so the silicon industry owned all the research in silicon. So researchers, when quantum computing came out, were looking at all these quite unusual materials. Now the Australian team said, hang on a minute, what's the best material to build a quantum computer in? We want something that has very high quality qubits, something that we can make right down at the level of single atoms so that we can do lots of calculations in the time frame that we can hold that quantum information. And so it dived into silicon when no one else was in there. And coupled with that pure materials characteristic of being a fantastic quantum bit or qubit, it is also manufacturable. You're piggybacking off 70 years of knowledge of how to make devices faster and faster in this kind of cycle of manufacturability. So that's really where the Australian team came in. They put out, very boldly, an eight-point plan. If we want to put a single atom in place and encode information on the electron on the atom, how do we put the atom there? It's something that we can't see. It's 50,000 times smaller than the width of a human hair, and it's beyond what the eye can see. And so they put out a plan, literally 8 points, how we're going to put the atom there, how we're going to make connections to it from the outside world, how do we know it's the atom that we've put there, and then can we turn it on, a transistor on and off. When that plan was put out, almost immediately IBM came out and said, well, look, that's great, but none of those individual stages has ever been done before, let alone getting all through 8 of those to actually make the device at the end. And they basically said, good luck, you Aussies, off you go. And so that was incredibly galvanizing for the team, I have to be honest, because it was like, a challenge. Everyone was a challenge to get through. In order to do that, we actually had to design the tools to make it as well. So it wasn't just this kind of process that we had to do. It was literally the tools, the scanning tunneling microscope that was normally an imaging tool. We turned it into a manipulation tool to put the atom in place. And then we needed another tool called molecular beam epitaxy, which is a crystal growth system that allowed us to encapsulate that phosphorus atom to make a nice, robust device. Anyway, so it's now history now. So it took us all the way through 2012. We got the first single atom transistor. Now, another kind of funny story for me, and amongst all of that, was when we got that single atom transistor, we're sitting in my office one day, and I got a phone call. And Michael Hart, who was the CEO of the Commonwealth Bank, had come to visit me. Now, this was quite a revelation for me. He was a very senior person from the bank. He knocked on the door and he said, I've been traveling all around the world. The Commonwealth Bank has been really good at its predicted cloud computing, and that's really helped the bank stay at the forefront. And I've been traveling around the world, what's the next big thing in computing? And I hear it's quantum computing. And he said, even worse, I hear Australia's doing a great effort. It's leading the world in this field. So I want to partner with you and see if we can do a project together. Now that, as a researcher, that's quite amazing to think that someone from a completely different sector has come in, I knew that we didn't have anything that was a computer that would be useful for him at that time, so it was quite confronting. So I was very honest with him. I said, well, we don't, we've just done our first device. It's got a long journey. It might be 10 years or more. And he said, that's all right. Let's work together and let's come up with a series of milestones and we'll partner with you and we'll see how that goes. Now that doesn't happen in many countries, I'll be honest with you. So that's a fantastic cultural thing that happens in Australia. And since that time, he really, for several years we had a project with him. He really encouraged me to keep pushing the milestones and to look ahead. We kept going for several years until 2017. About 2 or 3 years before, he said, right, what do you need to make the whole thing? And we literally plotted it out. We then raised $83 million. He came with us, with the bank, as a shareholder. He brought Telstra with him, Commonwealth Government, the state government, and the University of New South Wales, and we set up the company. And in that time, what we've done is we've systematically gone through, in much the same way as the 8-point plan, what are the things that we need to prove to show that we've got a really viable route to making a quantum computer. A very fast 2-qubit gate, how they operate together. A very stable system, very high fidelity, the lowest noise. We developed a technique where we could actually see the qubit with the scanning tunneling microscope. So we can actually see what the electron wave function, what does the qubit look like? Very few technologies in the quantum computing space know what their qubit looks like. We've got a team of physicists that help us mathematically model the energy levels of our qubits as we make them. And so systematically, we've gone through to get us towards that quantum integrated circuit. It's a hugely exciting time now, because now we're at that point where we can start to see our first product. So moving ahead, we've got a plan of how we're going to bring all these qubits together. We're going to correct for them as we build our integrated circuits larger and larger. We're looking at our first commercial product by 2026. We're looking at partnering with all these different industries now that want to use our system to solve some of their commercial problems. And so, what is it about Australian culture that allows us to do that? And that is something that, looking back on the journey that we've had, it really is that sense of having community, of taking on an ambitious project that very few people thought was possible, of not having any boundaries in the way that we think and allowing us to take on something that the rest of the world honestly thought could never be done. And so the next few years are going to be hugely exciting for us. We literally are going to build a quantum computing industry here in Australia. We've figured out how to manufacture and cycle through within a week or two each different chip design. And we've built the whole supply chain here. I'm very excited. I've got lots of my team members in the audience. We started out thinking we were just going to build the quantum chip. Now we're building the hardware that runs the quantum chip. So we've got some people that we've taken from the 5G industry, brought them across to us to make that computer go really fast. We've started building the software around about how we operate that chip. We have an algorithm team that looks at what are the problems that industry has that we can partner with and solve for them now. And so suddenly this idea from just making an integrated circuit is now literally moving towards commercial products that can be made here in Australia. And it's that manufacturing capability, that field that is transformational, putting atoms in place, doing calculations on those atoms, building a whole computer that can solve problems that fundamentally the world needs to solve in order to make it a better place. That's really what galvanizes the team. So all those young people in the audience, it is a fantastic field to be in. If you're not doing any kind of computing and physics, I definitely encourage you to do it. This field is exploding at the moment, and Australia is going to be a place where we can actually build the whole industry here. People from all over the world come here to be with us. So it's a hugely exciting time, and I encourage you to watch our progress over the next 5 to 10 years. So thank you.
Well, that was wonderful as anticipated, Michelle. Thank you. So my role, my name is Susan Bond. I'm privileged to stand here as President of the Royal Society of New South Wales. And my role tonight is because of the COVID restrictions, we are unable to have questions from the audience, but I'm sure Michelle will be happy to answer any questions after the formal part of the proceedings are finished. And I also have the role of providing the vote of thanks. And I note first that Michelle is a distinguished fellow of the Society, and you can see why. A wonderful presentation. you demonstrated both your scientific skills and your ability to communicate to a general audience. So I've got one question that's scientific and one that's more commercial. I noticed a year ago in August that you were featured in the Australian Financial Review Platinum 70 magazine, and you're asked to describe a time in your life that was transformative, scientific life, I would assume, and predict what might come next. And you talked about a moment 21 years ago when you combined two technologies that on the face of it looked incompatible, but when put together they actually worked. So can you describe that moment? Tell us whether the Nature paper is another moment, and then, as the magazine challenged you to do, tell us the moment when it'll change again.
Yes, sure. So the two technologies I talked about before, so this ability to image atoms, it's a scanning tunneling microscope. Some people in the audience will know this, but you bring down a very fine metal tip to where your atom is, and when you get close enough, under voltage control, you get a current flow. And what you do is you keep that current constant and you drag it over the atom, so you can trace out the atoms on the surface. So that was developed before us. That microscope allowed us to see atoms for the first time. But what we decided to do with that was to see if we could manipulate the atoms. And so there are many people have tried picking metal atoms up with metal surface just by putting a voltage on the tip and moving around. So we knew that basically we'd have to use that tool to pattern where the phosphorus atoms were going to go. But at the same time, we needed to encapsulate the phosphorus atoms to make them nice and stable. And that's a tool called a molecular beam epitaxy system. If I had them in the room, they would be, certainly the one we built at the beginning, they would be maybe each of them the size of this piano. Ultra-high vacuum systems, so you pump everything out. And one of them has lots of pumps to keep it very low vacuum system, and that vibrates away. That's the molecular beam epitaxy, the crystal growth system. And what we wanted to do was to combine that with something that's measuring atoms. So one's vibrating away with stainless steel, they're connected via a tube, and the other one is trying to image it. And so we figured out that we worked with the two companies in Germany, actually flew there, designed the connection tube between them so that the vibrations would not transfer. We designed a lab around it. The actual system itself cost $3.5 million, and the lab cost $1 million. So that gives you a sense. So it was a very high stakes decision to get these two technologies to work together. And certainly when we did it, the two companies said, we will build it according to what you want, but we don't give you any guarantee it's going to work. And that, as a young scientist, that's a huge risk, because then you think, oh my gosh, this is the end of my life. If this is the end of my career if this does not work. But as a scientist, I planned for the worst, did every bit of research we could, got those two technologies working together by talking to the engineers constantly, and then when it arrived, it actually worked about a factor of 6 better. So that was a transformational moment, because if it hadn't worked, I wouldn't be here today.
Right.
And I think the result that we recently had on the integrated circuit, that's more of again, lots of technical challenges, but things that people have never done before. So it wasn't going to be obvious that we would be able to do it. So it's just hard grit, laying out all the milestones and systematically working through. Our next one, I think I've got 2 or 3 actually. It's either going to be the first commercial product, which the team are very excited about, and it's literally how do you get that out and get it into use. That will be one. The second one is something called a logical qubit. So you can make these qubits, but they interact with the environment a lot and they're not very stable. If you make a logical qubit, you can correct for it. Very few people have made a logical qubit. That's the basis of building the whole computer. So that will probably be my second one.
Great. Okay, so when am I going to be able to buy a quantum computer? What will it look like? And will it be Australian made?
It will definitely be Australian made. Our whole thesis is it's Australian made. So everything we've done is to make sure that we manufacture here, and our manufacture cycle time is about a 1 or 2 week. It's about 15 to 40 weeks with other companies. So that gives us, I think, a competitive edge. It will be made here. I think arguably you could start working with this now if you wanted to. And so that's certainly what we're out there at the moment. So we're encouraging end users to come in, and we're plotting out the algorithms for them so we can work directly with them at the moment. And you asked 3 questions. I think I only answered 2.
Oh.
What was the third one? Do you know?
The third one was, what will it look like?
So it will, at the beginning, it will be like a server farm. So it will be in a cryogenic cryostat. So it's probably about my size or bigger, cooled to very low temperatures in a controlled environment. And we're building lots of those, so you can have lots of different chips in them. Eventually, that technology will probably shrink. But right now, it will be something about my size.
Right, so we'll be buying a refrigerator.
You would be buying, actually, it's a very good question, you'd be buying through the cloud access.
Okay.
In very much the way the original computers started out.
Great. Well, yes, certainly.
Now, for those who don't know me, you know I'm a dumb lawyer, and dumb lawyers ask dumb questions. So can I ask two questions?
Sure.
You talked about encryption and how quickly the quantum computer would be able to de-encrypt, is what I understood you to be saying, sort of codes. Is this moving us into a security risk, whether at sort of personal level in terms of personal data, but more particularly in relation to national security issues? So that's one question. Yep. The other question is, I got a little interested a little while ago in space law, and I found out about this stuff called space junk, which is whipping around the world, and the Kessler syndrome. You talked about the transport system and being able to sort of track the transport system and make it more efficient. With what are potential dangers with space junk and with so many satellites going up and some of them coming down? Will your area of expertise be able to predict the trajectories of space junk, perhaps even move the space junk so it doesn't crash into another bit of space junk and create more space junk, and or crash to the Earth, as some does. I know a lot burns up in the atmosphere, and that's what everyone keeps their fingers crossed about.
Yep. So look, let me go to the first one. So with data security, the big algorithm was Peter Shor's algorithm, which was code breaking, and that's why honestly lots of governments globally are investing in quantum computing, because anyone that gets one, the first one that gets one, will be able to do that. I think everyone that works in the field knows that to get to that point, you need many millions of qubits. We're all sitting around, the 0 to 100 qubits at the moment. And so there's a journey to go towards that. So people are at one level recognizing it's going to be at least a decade away before we can do that kind of research. And as a consequence, whenever there's a new technology, people are coming up with ways to offset it. So there's something called quantum hard cryptography. So a lot of classical cryptographers are figuring out how you can make it so that it's resistant against the quantum computer. And so there's going to be this interplay, in my mind, between software and hardware. As the hardware comes along, people will generate software to try and offset it. And those two are going to keep going, as in the classical industry for a long time. So yeah, it's open at the moment as to where that goes. On the space junk one, that's much harder. And so with the algorithms that exist out there at the moment, the optimization algorithms are trying to find out the optimal route for something. Eventually, I could imagine they could plot all the different satellites out there and their trajectories and then figure out where they're likely to collide. But again, that's going to take a while to do that. So one of the big challenges about quantum at the moment is how do you get data in and out? And so there's a classical chip that goes along with the quantum chip. That's kind of the next phase that we're working on. But yeah, those optimization problems, those are the kind of things that it will come and help with.
Great. The Society is privileged to enjoy the patronage of Her Excellency, the Honourable Margaret Beazley, ACQC, and to present in partnership this series, Ideas at the House. We thank you, Your Excellency, and we thank your staff for providing the opportunity for us to gather tonight here in person, as well as to live stream this wonderful presentation into houses and offices across Australia. In the old parlance of the Society, this is a true conversazione, and this is the concept behind Ideas at the House. I'm delighted to see in the audience so many new fellows and members of the Society elected during the pandemic, but unable to be presented in person because of the health restrictions. So it's wonderful to see in-person new fellows and members in the audience, and I hope that there are many more online watching. I'm delighted to see the high school students and also to welcome 6 students from the Sydney Quantum Academy who are here tonight to listen to Michelle's presentation and gain an appreciation of the work of Her Excellency and the Society. I point out to students that you are eligible to join the Society as associate members, so I hope some of you consider doing that. We're a wonderful organisation. And finally, of course, we thank Michelle for showing us, and I quote your hero and mine, Richard Feynman here, a theoretical physicist who wrote a wonderful, gave a wonderful presentation in 1959 about manipulating and controlling things at the nanoscale. And he concluded his article, or you may even entitle the article, "There's plenty of room at the bottom." And you have shown us that, Michelle. So thank you so much.
Thank you.